everyone. So I want to remind you that there's a homework too that is just posted on the Google Classroom. So again, please start to do working on your homework early. Some of you, it's almost like finish your homework at the very end. I hope that will not happen regularly. Okay, so I think in the last week we have very brief discussion about the formal structure of thermodynamics, and the strategy we take is to assume that the entropy is a function of concave. Is a concave function with extensive variables. So so in fact, that's a really mathematical, or to some extent cheating, in the sense that we didn't really discuss the microscopic meaning of entropy. Okay, so as I discussed at the very beginning of the lecture, that one of the purpose of statistical mechanics is try to give us a microscopic interpretation about what is entropy, or we can try to understand thermodynamics from a microscopic physics point of view. Okay, so so let's start today's lecture. So the purpose of the following lecture will be, we would like to introduce the fundamental postulate of statistical mechanics, and then we will try to explain what each term means, and why we choose this fashion, at least try to understand it through examples, why we choose to define entropy in this way. Okay. Okay, so basically we'll try to introduce the fundamental postulate of statistical mechanics. So I'll just write down what that is. So basically, this is the famous equation that is postulated by Boltzmann. So the first thing is that it is a postulate, which means that it cannot be proved. However, this expression is very useful for us to build some intuition about the microscopic meaning of entropy. So we'll try to understand the property of entropy using this postulate, and we hope that using this postulate and what we have learned from the last lecture about what is the thermodynamic entropy, we can see that these two concepts are somehow connected, or at least is a reasonable postulate that we try to think of entropy in this way. Okay, so so in order to understand that, we basically need to understand what every quantity means. So the first thing is about what's in the left-hand side. Is entropy is actually the thermodynamic entropy. Which is a macroscopic object. Okay. So why do I specify this as thermodynamic entropy? Is because if you read the literature, there are various different ways of defining entropy. In the information theory, the definition of entropy is something, and in the thermodynamic context, the definition of entropy is what we just discussed in the past few lectures. It needs to satisfy some of the properties in the thermodynamic theory, and it needs to give us the whole framework of thermodynamics by a very simple rule of the game, that you want to maximize this function as a function of extensive variables. Okay, so we know what's in the left-hand side, and the second thing that we need to understand is what do we mean by equality. Okay, so at this point you'll think that, oh, that sounds like a very weird statement. We already know what equality means. But at this expression, we need to be a bit careful, because what we are discussing is actually a macroscopic system, which means that we discuss a system where the degrees of freedom n is huge. Okay, so this equality actually means that what's at the left-hand side and what's at the right-hand side, they are equal in the sense that at the leading order of the thermodynamic limit, which means that at the leading order that n is sent to infinite. Okay, so please don't take this equality as the mathematical equality that we are familiar with since high school. Okay, so that's a tiny difference. And Kb is just the Boltzmann constant. To some extent, it appeared because of the historic reason, but let's just assume that it is just a constant that give us some like the correct dimensionality for the whole framework of thermodynamics. Okay, so nothing too much to discuss about Kb. And the last object that we want to discuss is what is this absolute value of gamma? Okay, so this absolute value means the volume of something, and what's the something is that basically it's the volume of gamma. Okay, and here this gamma is the accessible phase space. I'll be more precise. What do I mean by accessible? And then the next step that we need to discuss is what do we mean by phase space? Okay, so at this point we know roughly what this equation means, or what's the postulate. So let's try to think about what is the content of the statement starting from the very beginning. That is the phase space. Okay, so let's try to start from some simple system that we are familiar with. For example, a bunch of non-interacting particles. In this case, it's like the ideal gas model. So suppose we have a tank of ideal gas, and we have a bunch of particles inside. So to specify one particle, we need to specify the position and the corresponding momentum for that particle. Okay, so for a single particle, we know that if we live in a three-dimensional space, this position is actually a three-component vector. It contains x and y and z components. And similarly for the momentum. Okay, so for a single particle, at least we have 6 degrees of freedom. In 3D. Okay, so suppose we have n particles. In order to specify the microscopic degrees of freedom, actually what we need is we need the position for the first particle, the position for the second particle, to the position of the nth particle. And we need the momentum of the first particle, the momentum of the second particle, and all the way to the momentum of the nth particle. And this huge object, we are going to define it as a point in our phase space. So let me just define it as C. Okay, and this C actually is a 6n component vector. Okay. So the space where this Cassie lives is what we call the phase space for the ideal gas system. Okay. So that's basically, if we want to take a snapshot, and then we know where each particles are, and then at that snapshot of time, we try to measure what's the momentum for each particle, and then we basically specify uniquely what our system is. Okay, but at this point, of course, it is a very theoretical concept that we assume that we can do that, but in practice, we really have those information. Okay, that's for the first disclaimer. And the second part is that at this point, we are using a relatively simple model that's a bunch of particles, and we know that we can specify the mechanical property of those particles by just specifying what's the position and what's the momentum, and then we can predict how it evolves as a function of time in principle. So of course, you can say that, oh, maybe we are studying something that is not moving. For example, we can study a bunch of, random bits or classical spin, which points up or down. Then the phase space will be different. It will be constructed by the dynamical variables of your system. So in this case, if you are consider a bunch of spin up and spin down, then this orientation of your spin, it will basically be your dynamical variables. Then the space will be expanded by those configurations. So we'll discuss that a little bit later, but let's try to start with the ideal gas case and try to think about or try to understand what does that mean when we try to use the Boltzmann's postulate. Okay, so at this point, we give a specific definition about how we describe the microscopic degrees of freedom for a system. Okay, and we just discussed, we just use Cassie to describe it. So let me just try to draw. What do I mean by that? So suppose this axis is some kind of, the momentum of the first particle. And you have the position of the first particle. And in principle, there will be a bunch of other axes. Just to the nth momentum of the particle. The nth position of the particle. Okay. So the space that we are trying to describe is actually a huge space, because as I mentioned, there are 6 n components. So basically, I cannot draw it on the board. Even for n equal to 1, we need to draw a 6-dimensional space. So it's really hard to visualize. Okay, so I try to use this kind of conceptual picture to describe what does that mean when we use the phase space to describe our system. There's somebody waiting online. Okay. So once we draw our system in this way, then the vector Cassie with 6 components will be represented by a point in this really high-dimensional space. Okay. So how to specify what's the coordinate or momentum for this point is simply you just make a projection to the corresponding axis. But as I mentioned, this dimension is super large, so it's really difficult to visualize, but you can imagine by doing projection, you can specify what's R1, R2 to Rn, and P1, P2 to Pn. Okay. So so this is just one point in this phase space. It just means that we take a snapshot at time t. The next question we want to ask is that, of course, our system, if we try to describe it using the microscopic degrees of freedom Cassie, they are not going to be just one point stuck there forever. Basically, all these microscopic degrees of freedom will bounce back and forth. So they will exchange their momentum or exchange their position. So that means that this high-dimensional vector C will actually, move in a very crazy way in this high-dimensional space. Okay, so in principle, as the time evolves, this C will do some very complicated move as a function of time. Okay, so this path is parameterized by time t. Okay, so so in principle, if we try to start from the very general concept, we can ask how this system evolve as a function of time. Okay, so from the understanding of classical mechanics, we know there's a very useful formalism, basically the Hamiltonian formalism, that you can try to describe your system's Hamiltonian or total energy by considering your system might have some kind of kinetic energy. And those particles might interact with each other in some way. And that would be a very general description for this basically particles bouncing back and forth. Okay, so so one of the issue is this. Of course, you can see that it's very challenging to solve, especially when you include the interactions. But luckily, we are discussing about the ideal gas situation. So this U, basically, we don't need to worry about too much. Okay, so I just will try to write down the very general formalism. So maybe it might not be so complicated for the ideal gas situation. But from classical mechanics, we know that once we have the Hamiltonian and we know our dynamical variables are basically the position and momentum, then we can generate the equation of motion, basically describe how the particles evolve as a function of time. So basically, why there's a, does that mean I need to end my course earlier? So this is the equation of motion for our system. Okay, so in principle, we can always use this formalism, but the problem is this coupled differential equation might be very complicated to solve if there are interactions. But at least we know that there's a principle that we can evolve our system, and this is called the canonical evolution. Okay. So now we are using very general settings to describe our systems. Maybe I'll stay here for a while and ask, are there any questions so far? So if not, let's try to use some simple examples to get a feeling about what are these phase space concepts. Okay, so usually I will encourage everybody to try to think in the simplest case and try to start from there and try to go to more, complicated situation. So in this simple scenario, we are discussing about some kind of particles. Of course, when n is like 10 to the power of 23, it's impossible to imagine what that is. But at least we can start from n equal to 1. Okay. For a single particle, we know that the space that we need to discuss is basically formed by the position of this particle and the momentum vector of this particle. Okay. So consider we are starting from the free particle case. Okay. It should be relatively straightforward because we can try to think, maybe there's a momentum P1, and by definition, the free particle will only move in a constant momentum vector. So it must be moving along some straight line with constant projection to the momentum axis. And of course, its position R1 will be different as a function of time. So let me try to write down. P1 of t is just some P naught vector, which is a constant in time. And the position of R1 of t is the initial position plus the velocity of this thing, which is E1 divided by M1 times the time t. Let's assume that we start from t equal to 0. Okay. So that's the simple case for free particle that we can imagine what that is. So we can try to get to a more complicated situation, that's n equal to 2. Then instead of R1 P1, we need R1 R2 and P1 P2. Okay, suppose we are still discussing about the free particles. But now, as I mentioned, now we have two momentum axes, and we also have two position axes. Wait. Okay. And for our two particle system, our system in this phase space will be still characterized by one point. But now this point will be specified by this very long vector. So each one have 3 components. So total you will be a 12 component vector. Okay. And in principle, it will evolve as a function of time, but now it becomes very difficult to visualize on the board because we require this particle to have constant projection with, to the P1 axis and P2 axis. So it is not easy to visualize in the usual 3-dimensional space, but I hope you can try to do that. One trick is that you imagine that P1 is one of the z-axis and P2 is some kind of, I don't know, x direction of that, and your particle is moving in a fashion such that its projection to these two axes is basically a constant value. Okay, so that's already a little bit complicated. Then you can imagine that when n goes to a large value, it will be very difficult to visualize. Okay, so now we have a rough feeling about how to describe our free particle systems in this phase space. One of the important example is the simple harmonic oscillator. Okay, so again, let's start from the one particle scenario where we are able to imagine everything almost exactly. So we still have a space labeled by a momentum and position. And the Hamiltonian for the simple harmonic oscillator is basically this Hamiltonian. Okay, and since energy is conserved, so we require some constraint about the evolution of our system. So now, since P1 and R1 are a variable, so we immediately can see that this expression corresponds to some kind of oval or the ellipse that we have learned in high school. Okay, so so that's how simple harmonic oscillator is described in the phase space. Basically, you start from some initial momentum or initial position. Let me denote it by R naught and P naught. And the system will start to evolve. But the way it evolves is basically you need to satisfy the energies, conserve the constraint. So what it is doing is that in this phase space picture, the system is, if we represent it by a point, this point will just surround the origin and make a eclipse motion. Okay. So again, if you try to think about that in higher dimension space, it will be relatively complicated. But from those very simple observations, we can notice something that at least if we start from the energy conserving point of view, like the free particle where we have constant kinetic energy, or like the simple harmonic oscillator, we found that actually this constraint reduce the degrees of freedom from the 6n independent degrees of freedom to 6m minus 1 independent degrees of freedom. And the reason you have this minus 1 is because you have the conservation of energy that can help you. Okay, so now they are not independent because you can construct the canonical evolution for your system. And because of this conservation of energy, actually the dynamical path of your system actually will be parameterized by a single parameter t. So to some extent, the dynamical path of your system in the phase space will always be described by a line, and this line will be described by a single parameter time. Okay. Questions? Okay. So let me try to draw that. Okay. So that's basically when we try to use this specific example to understand what's going on. Okay. So now one thing we can notice is that the space is basically a really high dimensional space. That's one thing. And because of that, if we try to make the following observation, that suppose we have some point, basically our initial state of our system. Let's describe by, let's see, did I write it down? Yes. Basically, I of t naught is t equals t naught. And our system might evolve to here. Okay. So, so in this space, if we assume that there are some deviation for each particles, for example, deviation of the position of the ith particle, let's assume that everybody is deviated by some amount, basically delta r. And also everybody's momentum is deviated by some amount delta p. Then we can ask what's the difference between these two vectors. suppose this difference is called capital delta, then we can simply describe it by the square root delta R square plus delta P square and sum over every particle. Okay. So you can see at this point, if delta R and delta P is some fixed number, then this delta will be some quantity that is proportional to square root of n. When n is large, it means that this difference will be a big number that's much larger than 1 under proper units. Okay. So now we kind of have a rough feeling about how the system evolves, at least from the microscopic point of view, basically because those particles collide with each other and they exchange momentum with each other. So this high dimension, this phase space point, which represent our system, will evolve in this high dimensional space in a very irregular way. Okay. But we also know that when we try to measure a thermodynamic system, we can measure the volume of our system. We can measure the energy of our system, and usually we did not observe this kind of crazy fluctuation, at least at the macroscopic world. Okay, so that means that the thermodynamic quantities must not be sensitive to such a microscopic configuration change. For example, this deviation delta. Okay, because if it does, that means like the observation at the macroscopic world actually will fluctuate very wildly. Okay, so that's one thing if we try to build the connection between the microscopic and macroscopic world. Okay, so that's one constraint. Okay, so now we roughly have an idea about what is the phase space. But as we mentioned, in order to describe our entropy, we need to have an understanding about what do we mean by accessible, because we need to define this quantity, which is the volume of the part of our phase space. So let me try to give a relatively simple example about what is the accessible space. So suppose we have some kind of piston, and initially we have some gas inside this the tank of this piston, and there's some pressure outside and there's some pressure inside. And initially, along the x direction, the tank has length is described by a length Li. Okay. So suppose P1 is smaller than P out, which means that the pressure outside will try to move this piston to the left and compress this chamber. So at the very beginning, like the initial situation, if we try to draw the phase space, let me just try to focus on one of the axes, which is x. And of course, there are tons of 6n degrees of freedom that we need to fully describe this phase space. But if we just look at this cut along this x direction, then we know that because this chamber is limited within this region, so the position of these particles can only live inside this small region. Okay, because there's no way that the projection will be outside of this X region. Okay, so basically I think what I should be more careful about is that this X represent all the possible position of our particles, okay? Because all the particles can bounce back and forth, but they just cannot escape from this chamber, okay? So now, as we mentioned, the outside pressure is larger, so the chamber will be compressed to a smaller system size with, I don't know, LF. So maybe this is the final situation. Then the phase space will be changed. Now shrink from 0 to Li to LF. Now the system can only, evolve within a smaller region in the phase space. So roughly, that's one of the possible way to imagine that what do we mean by accessible phase space. In this case, it's easier because we restrict our system to be described by some chamber. So the restriction about the coordinate of our system is easy. You just ask it to sit in some space region, okay? But in the case, of course, you will say that, oh, this is just a very special case. Maybe we will consider other case like free particle. In that case, how should we restrict our accessible phase space? Then another important ingredient that I did not specify in this simple case is that usually we consider the concept of the energy case. Then energy will impose some other restriction to your accessible phase space. Okay. So now you can see that in our system, of course, there are various different kind of constraints. Then those constraints will basically used to reduce the accessible phase space and change it, the description of your entropy. Okay, so I think that's our first visit about what do we mean by accessible phase space, but we will have a more specific definition later. So at this point, are there any questions? Yes.
If we analyze the field with the new standard deviation.
Yes.
I am still very confused about the deviation.
Okay, so that's a good question. So actually, at this point, I'm just trying to demonstrate what's the property of this space, but not specifying about, special physical realization. And the reason I want to say there's the deviation is trying to emphasize that because the dimensionality of your system is really huge, that's basically this summation over I goes from 1 to n. So if you require your the accuracy of your system, for example, like you have a bunch of atoms in your chamber, but when you take a picture, you cannot have the 100% accurate position, and maybe your measurement has some error, like delta R or something, right?
So it's just a perturbation of R and P.
Yeah, it's like just a mathematical concept that if you have some kind of measurement that's not perfect, maybe you can only measure your position to the accuracy of delta R and measure your momentum to the accuracy of delta P. In this high dimensional space, what kind of effect it would give you? So basically, it will tell you that your error or like the distance within this space represent by the true system's configuration, and the measure the system configuration actually it's has a distance that should be proportional with square root of n. And when n is large, that actually means that this deviation could be huge. So in order for it to be, for our system to have some thermodynamic property that's not fluctuating too much, that actually means that this delta needs to have some scaling property to your system. Otherwise, you will be not very a smooth function. if we try to interpret its thermodynamic property. Yeah. So it's just a mathematical structure for this phase space, and try to have a rough idea about what it looks like. Okay, good. Okay, so now I think we have talked about the constraint space. Now we are going to introduce another very important concept, which is called observables. Okay, so at this point, these observables, I need to emphasize that this is a little bit different with what we have learned in quantum mechanics. Okay, so quantum mechanics, what we meant by observables is that those things are experimentally measurable and has these physical quantities usually have real eigenvalues such that you can measure it. Okay, so that's like the definition of observables in quantum mechanics, and we specify these observables by some Hermitian operator and things like that. But here, the observables have another meaning. So let me try to describe what do I mean by that. So as we mentioned in the previous discussion, that in our very high dimensional phase space, by the way, I think maybe I did not really specify that carefully enough. So let me try to write it down somewhere. So now let me try to use a shorthand notation of this R to represent the positions of these M particles, and this little p to represent the momentum of all the M particles. So basically our phase space will be represented by this R and P vector, and each one of them will be a 3n component vectors. Okay. So if we have a system with the initial states somewhere here, represented by a point, then you will have its evolution in some really complicated fashion. And maybe, as we already mentioned, that under certain physical condition, we restrict our system to only be able to evolve within some restricted space. Okay. So what do we mean by observable is that observables are basically those functions. Let me denote it by O. And this O is a function of our system's microscopic degrees of freedom Kc. Okay. And basically, it will map this Kc into some value related to this O. And when the system size is large, as the time evolves, if this O of t, which is, maybe I should write it more specifically, O of Kc of t, usually it could be something that is fluctuating. Okay. So what do we mean by observable is that we hope that this function actually will give you something that is more or less smooth as the system is evolving. So if this kind of function exists, we said it is a observable. Okay. So at this point, you probably can see why do we want to define this observable, because we want to make a connection between our microscopic degrees of freedom with the macroscopic quantity that we can measure. Okay, so I think I'll stop here, and we'll start from this point after 10 minutes. See you in the next lecture. So I think we'll continue with some good questions I got during the break. So the first thing is that I think I did not explain very clearly what do I mean by the accessible space in this example. Maybe I went through a little bit fast, so let me be more precise. So when we have a bunch of particles inside our chambers, right? Maybe we have several particles inside our chamber. So we can ask what is the coordinates for our particles, right? because those particles are all inside the chamber, so their coordinates must be within 0 to Li, right? So, but if we try to draw that in the phase space, as we mentioned, our system is only represented by one point, and the coordinate for the first particle will be the projection of this point to the first coordinate R1, and the coordinate of the second particle will be this point project to the coordinate direction R2. Okay, so every R1 and R2 is represented by this x-axis coordinate, and the constraint that every particle needs to sit within this range of the chamber, basically this range, require this projection to be within 0 to Li. Okay, so if you have particle that's for some reason that's leak outside of the chamber, then the region that's greater than Ri will be accessible. But in this case, we assume that this chamber is completely sealed. There's no leakage of particles. So this region outside of Li and the region that is smaller than 0 is basically inaccessible region. Okay, at least from the coordinate from the coordinate part of our phase space. So why do I choose to use coordinates to represent this idea is because usually when you consider momentum, it requires some other understanding about your energetics. So it might be a bit more complicated. So in this case, it is kind of obvious because the way you allow or disallow some of the phase space region is simply using this chamber. Okay. So so in the final stage, that is basically when the chamber is get compressed by the external pressure. That means that the inaccessible region becomes larger, and the accessible region will become smaller because now it only allows the particle to stay in 0 to LF. Okay, and of course the momentum part we don't know what it is doing at this moment, but I just want to use the position part to demonstrate what we mean by constraints given by the system. Okay, so that's one thing, and the other thing is a question about in the previous study about the probability theory, we said that maybe we have a set, and this set have various different events, and we can ask what's the probability of a certain subset of the events to happen. Okay, so one question is that when we define this phase space, how it is going to be related to this kind of probability concept. At this moment, it is not clear, but it will become more transparent afterwards. But at this moment, I think what I can say is that here the accessible phase space volume is specified by our physical condition. Maybe like the volume of this system is given, or like maybe the energy is given, so you will get a phase space volume specific value. And then when the system is going from one configuration to another configuration, for example, you put two systems in contact, and when they reach thermal equilibrium, then this physical observable like energy or the volume will change from one point to the other. So in the middle, you will have a lot of different configurations of energy and volume. But for those different points, you will have different accessible region of your phase space. And those will form a big set. And this big set will be related to some of the probability interpretation. Okay. But later we'll see that actually there are some very interesting structure behind, such that we can try to construct this probability interpretation. Okay, so let's continue with the concept of observables. So we define observables to be basically a function of this microscopic degrees of freedom c, and we require this function to be somehow smooth enough such that when the microscopic configuration is evolved as a function of time, this observable or this function O is still smooth enough such that we are able to measure it. Okay, so that's basically the idea of these observables. So let's try to illustrate some of the examples to get a rough feeling about what we mean by observables. So the first one is the total kinetic energy. Okay. So it should be simple because we have particle from 1 to n, and the total kinetic energy just means that we sum over all the kinetic energy together. Okay, let's assume that the mass of the particles are just identical for simplicity. So so we can ask a question. Suppose one of the particle have some change of momentum. For example, let's assume that the first particle's momentum goes from P1 to P1 plus delta P. Okay, so that means that the energy for the first part, the kinetic energy for the first particle, EK1 will becomes EK1 plus some delta E, and this delta E is related to the change of momentum of this first particle. And let's suppose other energies, other particles still have the same kinetic energy. Okay, so the total change of the energy, if we just change one of the particles' momentum, will basically be something. Basically, wait a second. Let me just divide it by the total energy. Will be something that is proportional to 1 over n. Okay, and the reason is somehow kind of obvious, because if all other particles are not changing, when you just change one of the particles' energy and you increase the other particles without changing its energy, then basically this relative change will be a function that's proportional to 1 over n. Okay, so when n goes to infinite, basically this quantity will shrink to 0. So that means that this total energy will be somehow smooth enough if you try to make a small change of one of the energy of your particle. Okay, so now let's try to take another example, which is a counterexample that it should not be a function of observable. That's basically this capital theta. It is a very artificial function, because usually in order to construct something that is not observable, usually means that it is not something that can be probed experimentally. Okay, so here theta function, we are going to use that frequently today, will be 1 if the argument is greater than 0, and it will be 0 if the argument is smaller than 0. Okay, so this is a very simple function, but if you try to evaluate this function for every position of the particle, and this expression just means that in order to have this theta function to have non-zero value, the position of the particle needs to be sitting within a ball with radius r0. Okay, so that means that let's try to draw a ball with radius r0. Okay, and if every particle is sitting inside this r0, that means that this theta function, this capital theta function, will be greater than 0, or it will be 1. Okay, but if in case that most of the particles sits inside this ball, but one of them is sitting outside of the ball, then this theta function, capital theta function, will become 0. Okay, and this capital theta function is not scaling with your system size in any way. So this change is actually a 1 to 0 change. It's basically a huge change that cannot be dropped when n goes to infinite. So that means that this capital theta function actually cannot be considered as an observable according to our definition. Because as the microscopic degrees of freedom changes, it could have some dramatic change. Okay. So you can try to use this kind of argument to convince yourself that actually internal energy is also an observable. And the total particle number is also an observable. Okay. So now we have more or less a well-defined concept of observable. We are going to postulate that all the extensive thermodynamic variables in the fundamental equations are observable.